Alright, welcome. In this video we're going to take a look at another problem, a very common problem related to scheduling that actually has a number of different variants. We're going to use this again as a backdrop to continue talking about greedy algorithms. So our goal here is to one, again, study an algorithm, but also use that as a way to study a technique that we could apply to, say, a novel problem that we might encounter. So to begin, I wanted to start with, again, sort of a loose definition of the problem, an informal definition, something that you might be given, maybe by a customer or your boss. So in this case, my example says maybe you've been hired by the School of Engineering and Technology, that's where I work, to assign some courses to classrooms next quarter. This is a very standard kind of problem that you face while at a university, but in other sort of situations as well, where you have resources that you have to assign to a particular, whatever, classrooms, printers, computers, processors. There's lots of different things that you might have to schedule tasks to, and then maybe those tasks have specific times that they need to be carried out. So in this case, we're assuming they're classes. And then we want to assign our classes to classrooms, following a fairly standard constraint that makes sense, which is no two classes can be in the same classroom at the same time. But two classes can be in the same classroom if they're not at the same time. That makes sense, right? And so if we want to follow that sort of standard real-world constraint, then usually the goal is, well, what is going to be the minimum number of classes that or classrooms rather, that we need to use to schedule all the classrooms, or what are the minimum number of printers used to print all the jobs, or the minimum number of processors necessary to process all the tasks, whatever the particular real-world version of this might be. We often call this problem interval scheduling, and again, it has a number of different versions. And so the version I've got here is sort of one version that's maybe not too tricky, but also not too simple either. Okay, so the problem that I have posed here is, well, can we take this informal definition and formalize it? Well, let's see if we can try and do that. Okay, so let's consider, I've decided to call it interval scheduling. Again, that's sort of the common name. If you want to go do a quick Google run by Wikipedia, you can go find some more information on it. And like I mentioned, there's a lot of different versions of this problem. So if you do jump through to Wikipedia, probably the first thing you're going to find is it's going to say, well, which one do you want? So it might take you a minute or two to find out which one you want. Well, let's try and formalize our problem ourselves into one setup here. Now, so let's think about, well, what was the input? What were they given to us? Well, in the slide there, I didn't really indicate. Let's maybe jump back here very quickly. Each one of these sort of horizontal bars here, I was sort of using to indicate a class, and I meant this over time. So the left-hand side is the start time, the right-hand side is the finish time. So each of these we can think of, one of the reasons we call this an interval scheduling is we can think of this as an interval of time and then a smaller interval and so on. And we need to schedule these intervals to, in our case, classrooms. So when we're thinking about what the input to the problem is, really we've been given that information. We've been given the start and finish times. And there's a couple different ways that we can formalize that. And I've actually gone through a couple different ways to formalize it in the past, but I think the way that's going to be most helpful for us is to use some set theory. So I'm gonna make a set, and I'm gonna call it C, and since it's a set, it's gonna have curly braces here, and it's gonna be a set C of classes. Okay, but what's important about the classes? We don't care about their name, we don't care about who's teaching them, we don't care about the students in them, we care about the start and the finish time. So I might do something like this. I might say, okay, a class is going to be a CI, but I want to say what it is. A CI is actually going to be an SI and an FI for start and finish. And maybe I'll say here just sort of briefly, well, what range of I do I have? Well, let's say there are n classes, and each class CI is a pair, a start time and a finish time. And so I might say here a set of n classes. And if I wanted to go in more detail, I could say talk about the start and the finish time. And if we are going to be very precise about the start and the finish time, we might say such that this is again a standard and obvious sort of assumption. SI should be less than FI. And here I've sort of chosen to leave out the case that it's equal to, the start and equal to, that means the class is 0 minutes long or 0 hours long. That doesn't make sense, so I'm going to assume that each class has some positive length. So again, this is just adding a little bit to be a bit more precise. This is something that we might assume given our standard assumption about how classes work, for instance. Okay, let's continue. Now, the problem, just like other problems we face, this is a optimization problem. So one of the things we're going to have is a min or a max. So I'm going to, in this case, it's the min. M, I'm going to say the minimum number of classrooms. And we have to add something else, not just the minimum number of classrooms, but we want to know how to assign the classes to classrooms. So one thing we might want to put here is something like an assignment of classes to classrooms. Now there, we're being a little bit vague, and we're waving our hands a little bit at the word assignment. What do you mean an assignment? Now, I think most of us have this intuitive, natural understanding of what an assignment would mean. It would mean each class gets assigned to one room and only one room. And then we have to add the additional criteria that there's no overlapping times. That was the part that we started out with. So we could write down here, okay, each classroom is assigned to exactly one room and no more rooms, and then the non-overlapping bit as well. But there are some mathematical words or terms that we can borrow that actually carry on carry out those two different characteristics that we're trying to capture there. Now, the word that I'm looking for here is a partitioning. Okay, so we've got a set here, and to partition your set is to split it up into subsets. Okay, special subsets, two subsets. So maybe I'll come down here and I'll give us a definition. Partitioning. So partitioning of a set S means by definition split S into mutually disjoint, so here's one thing we were talking about, and together exhaustive subsets. So again, borrowing more terms from set theory, what does mutually disjoint mean? That means if we take any of the subsets that we split S into, and we take the intersection of the two, say we had subset 1 and subset 2, then the intersection should be the empty set. That's what disjoint means. And mutually disjoint means that if we did this for any I and any j, that would be true. Together exhaustive means take the union of them all, I equals 1 to n if there are n of them, of our SIs, and we get S back again. Now these two terms are the set theoretic way of saying that the mutually disjoint says don't assign a classroom to more than one class, and the together exhaustive says assign one class to every classroom. No, I got that backwards. Together exhaustive means that we need to, together exhaustive means if we take the union of all of the sets, we get the original set back again. That means every class has been assigned to at least one classroom. So we've got both of the properties that we were looking for here, all with this one expression here, partitioning of a set S. And in fact, here I've been sort of agnostic to how big it is. I guess I called it n here, but usually let's change that. Let's call it m, since n we've sort of already used, and m is the size that we actually want. So we could do an m partitioning if we split S into m mutually disjoint and together exhaustive subsets. So that's what we're going to do here. So m is the minimum number of classrooms that we want to want to find. And then we want to partition our classes into m subsets that are mutually disjoint and together exhaustive. So I might say here, and an m partitioning of C into, and then the m partitioning part captures this bit, so I don't need to do this bit anymore, but the part that I want is the non-overlapping bit. So I might say here into, so an m partitioning of C into non-overlapping. Now that captures the fact that we don't want any of our two classes to occur at the same time. And that part isn't captured by just this set theoretic term, m partitioning. Okay, so again, we've just gone through sort of that first step of trying to formalize our problem, give us something to talk about even. So now that when we want to write our algorithm, we have things like our SI and our FI. If we want to talk about that, we can talk about M. We've already brought in these concepts of an M partitioning. That might be helpful in our algorithm because that's what our output should be, right? We're trying to partition our classes in this way. All right, I think we've got our formalization pretty much the same. Here I gave the m partitioning a name P. I guess that's going to be helpful. Okay, also useful in the end. But then I've posed myself another question. If these are the classes that we have to schedule, the way that I've got them drawn here, I put some effort into making them look like the enterprise, but I also put effort into making them be a couple counterexamples, as we'll see in a bit. The way I've drawn it here, because I've drawn them in these sort of horizontal lines here, each horizontal line could be a classroom. So we could assign these two to one, these two, and so on. So any of the classes on a horizontal line are all going to be sort of non-overlapping. That's the critical part here. Remember in previous videos I talked about the criteria of validity and optimality. For most of our optimization problems, we're going to have usually two criteria that we need to satisfy for our output. One of those criteria is going to be a criteria of validity, and the other one will be the criteria of optimality. Okay, now in this case our criteria of validity is the non-overlapping bit. Okay, that our set should be non-overlapping. So if we have assigned classes to a classroom, they should be non-overlapping. But then there's also a little bit of the validity coming in with the M partitioning. We want our assignment to assign every class, and we don't want to assign a class more than once. So those are the validity bit. The M, that's the optimality part. So we could imagine there's some assignment of classes to classrooms that is a partitioning, maybe not an M partitioning, but is a partitioning, and all of our classrooms are non-overlapping, but maybe we don't achieve the M. We get something else, something bigger than M for our partitioning. That would be a valid output, but not necessarily an optimal one. So what we have here is a valid assignment of classes to classrooms, and it uses 1, 2, 3, 4, 5, 6, 7, 8, 9. So the question here is, can we do better? And I think maybe it's not too hard to see that these two classes here that are sort of isolated don't need to be isolated, and by moving them sort of up here, we can see that at least we can do 1, 2, 3, 4, 5, 6, 7 classrooms. And the question that maybe remains is there any way that we could do this with fewer than 7 classrooms? And that's a harder question to answer. Because remember, if we want to do that without being clever, we have to brute force through all possible assignments, and that's a lot. I don't want to try all possible assignments. And even right now we might just think, well, could I move something here, maybe move something else somewhere else? Is there any possibility that I can move a couple around to make this work? Now actually, if you're a little bit clever, you might notice if you draw a line right here, I think I got that right, we get 1, 2, 3, 4, 5, 6, 7 classes that are all overlapping with each other. And that's probably a good sign to us that says there's no way that we could put those 7 classes all in say fewer than 7 classrooms without an overlap. And I think we could try and do that over here too, but maybe it's hard for me to see if that orange one actually overlaps with the black one. It looks like it maybe doesn't. So over here we maybe have 6 and 6, so we might be able to do something. If we didn't have this problem over here, maybe we could move the black one down here, for instance. But it looks like, yeah, 7 is probably the best. So at least for this input, just eyeballing it, maybe we've got ourselves set up with a good setup. But of course the problem here is, in general, for any set of classrooms, or sorry, any set of classes, can we come up with the minimum collection of classrooms? Okay, well, let's see if we can continue by solving that problem. Again, take a look here on Wikipedia if you like. Like I mentioned, there's many versions of this problem, so the main problem that is studied in this link is not necessarily the one we're looking at here, but might give you a good stepping stone to find the one we're looking at here. Okay, now here I want to, again, this is something we maybe could have started doing in some of the earlier videos, but here I want us to start out by saying, imagine now that we've been given this problem, but we don't really know what strategy to use. Here I'm going to focus on greedy, but the thing with greedy algorithms is there's often going to be more than one candidate algorithm that comes to mind. And that's usually because they're somewhat easy to think up. Also, as you get a little bit of experience with this, you'll notice that you know, the first one you think up, the easiest one you think up, is not always necessarily even correct, or if it is correct, not always necessarily the best one. So imagine you're sitting with your colleagues, maybe at work, or maybe you're a student, and these are your fellow students, and you're sitting around and you're trying to say, okay, what kind of algorithm can we use to solve this problem? Again, keep in mind, this is a real world problem that universities need to solve every quarter. So whether you have an algorithm or not, you might actually just have to solve the problem. There are real people out there in the world that just need to assign classes to classrooms, and so they might be sitting down saying, how should we do this? So here we imagine 2 possible ways of doing this. And I've set these up as greedy algorithms in the sense that I'm stating them as simple sentence, because greedy algorithms are usually so simple that we don't often need to set up pseudocode. We might, but usually they start with just a simple idea that can be summed up in a single sentence. So let's look at our 2 algorithms. I've attributed them to our friends Alice and Bob, who sort of regularly show up in computer science examples. And I've also sort of named the algorithm a little bit based on sort of how the algorithm works. So Alice's algorithm I'm going to call the first fit algorithm, because it's going to basically place the class in the first classroom that it fits in, okay? But with a little bit extra going on to it. It says select the class with the earliest start time and place it in the first compatible classroom. Now, there's an assumption here that is an assumption that we'll usually use in a lot of greedy algorithms, which is what we mean here is repeat this until you're done. So it says select the class with the earliest start time, place it in the first compatible classroom, then delete it from the set and do this again. Find the next class with the next earliest start time and place it in the first compatible classroom. So there's 2 pieces to this algorithm I've sort of highlighted here. One, we need our classes in this order, and this is something we're going to see in a second is critical. We need our classes in the order of start time, but once we have them in that, it's a fairly straightforward algorithm. We go one at a time and we just find the first compatible classroom. Now, this is being a little bit agnostic here, and we'll see when we try and struggle with this algorithm in a second, that there might be more than one compatible classroom. So when we say the first compatible classroom, that's saying really just the first one you find. There doesn't need to be something special about it. Anyone will do, so any compatible classroom might be another way we could state this. Okay, but then I didn't really want to call it the any fit algorithm. Maybe that would work too. But first fit sort of is a conventional name that we use for these types of greedy algorithms, where we just put it in the first place it fits, or the first location that it's going to be a valid solution. then what we really mean here is an arbitrary or any compatible classroom, which means we're not going to put any extra decision making in to finding a compatible classroom. It's merely going to be binary. Is this compatible or not? And when we find it, boom, we're going to jump in. Now, with that said, we might sort of blend these two algorithms. We'll see in a second. We might want to find the first compatible classroom. No, maybe we want to find the compatible classroom that our class fits best in. That would be a best first fit or something like that, or maybe just a best fit, Alice's best fit algorithm. That would be a different one, but as we're going to see, that one is going to have the same performance, so it doesn't matter. We could put it in the best one it fits in, but we don't need to. Okay. Let's look at Bob's algorithm here. Bob's got a slightly different approach, and this approach follows a very common strategy for some algorithms, and maybe I'll point out another one. If you've had any experience in retail, if you've ever had to make change while you're exchanging money for goods, then there's an algorithm we use in most countries of the world because our currencies are designed in this way that this algorithm will work. It's a greedy algorithm that if you want to make change and you want to minimize the number of coins or bills that you need to use, you choose the largest coin or bill that you can use to make change. And if you repeatedly follow this strategy, you will minimize the coins. And this works in all of our coin systems, but it doesn't work in all possible coin systems. But we've designed our numerical or our currencies to work with this algorithm. But the strategy behind this algorithm is if I want to minimize something, the number of coins, one good strategy to do that is to sort of take maximum size chunks out of it, maximum size bytes out of it. So in this case, we're going to use the biggest size coins to sort of minimize the number of coins we can do. Well, this is the idea behind sort of Bob's best fit algorithm too. Here we want to minimize the number of classes, so maybe we can achieve that by maximizing the number of classes we put in a single classroom. Okay, so he says basically find the largest set of classes that are all compatible with each other and just put them in a classroom together. And again, in that way, we've sort of taken a maximal size scoop out of our classes we need to categorize. And then what's left is the smallest chunk that we're left with. So after each time we do a scoop out of our classes, we're left with the smallest size chunk left. Again, the idea here is one that works in other cases and might work here, is the idea that if we take out maximal size chunks, we might get the minimum size number of chunks at the end. So the question then is, we're sitting around the table talking to Alice and Bob, which algorithm should we use to solve our problem? And usually a good answer to this is, well, we should try them both out or all out if we have more than one. But how do we measure them? How do we decide which one is the best at the end? So the first criteria we typically use is correctness. Are the algorithms correct for the problem? So we should be looking for a proof of correctness if we can find one. If we think they're correct, of course, we usually propose algorithms we think are correct. So look for a proof of correctness. But, and I recommend this as sort of just advice if you're ever stuck in this position, I recommend doing both, finding the counterexample and the proof of correctness at the same time, sort of going a back and forth. And the reason is, like if you ever get them presented in a class or a book, usually it just looks like whoever created it found the proof of correctness perfect right where it was, but that's not really how these things work. Usually you struggle with the proof of correctness and you try and wrestle with it and try and make it work, very much like writing a program. It doesn't work the first time you write it down. And also, if you're starting out and you don't know if your algorithm is correct or not, you might struggle with the proof of correctness for days and days and turn out that it's not correct. So usually it pays off to put at least some effort into the other direction as well, because we don't know which one is going to pay off, and only one will pay off, of course, right? So what that usually means is I try both, and counterexamples tend to be a little bit easier, so sometimes I might start there, but these algorithms look like they're correct, so I might start on the correctness side if I'm fairly confident. But going back and forth can help. So maybe I start writing a proof of correctness, and I get to a case where I'm like, oh, this is a tricky case. I don't even know if I can write a proof for this case. So I say, aha, maybe I found my counterexample. So I jump over and I say, let's see if I can use this tricky case and design a counterexample that will make my algorithm not work. Now maybe in struggling with that counterexample, I'm like, I can't get it to work. I can't get it to work because they're always lining up perfectly. Oh, that's exactly the argument I needed, exactly the piece of the puzzle I needed to finish my proof of correctness. The reason I can't find a counterexample is because they line up exactly perfectly or something like that. So again, I'll often go back and forth between these two because struggling with the other direction can help you fill in the blanks in the one that you're working on. Okay, so that's one. And again, if our algorithm is not correct, usually that means we need to discard it right away. Although there are some degrees of correctness, and that's part of why I want to look at these algorithms here. Even if an algorithm isn't exactly optimal, it might be close to optimal, and we'll see that in a second. Okay, say they're both correct, then our second measuring stick then is, well, which one gets us to the finish line the quickest? Which one's most efficient or uses the least number of resources? And actually, our two algorithms here are going to be a little bit hard to analyze the resource use without fleshing them out a little bit more in pseudocode. So we'll probably want to do that. All right, so I want to start with Alice's algorithm. And I do want to start with some pseudocode for it. Now this pseudocode is not going to be very challenging. Again, most of the time we get away with describing the algorithm in a single sentence. But our goal in coming up with this pseudocode is to give us something a little bit meatier to bite onto during our analysis. Okay. The first thing we probably should notice, and if our aim here is analysis, then we notice that we need our classes in order of start time. And if naively we just, every time we need the next class with the earliest start time, we just search through the list, we are aiming towards an n-squared algorithm here. So we might, often what we're going to do here is we're going to do something called a pre-sort. The first step of the algorithm is effectively just to sort the input. And often in a lot of these pre-sorting algorithms, that's the most expensive part of the algorithm too. We just pre-sort and then maybe iterate over the list. So the pre-sort maybe is an n log n, and then iterating over the list is maybe order n. Okay. Now our algorithm here is not going to be that simple, but it's going to at least have that structure. So let's take a look at the pseudocode to start out. So called it first fit, and I'm taking in our input here. And again, I mentioned that maybe our first thing to do is just sort the set in ascending order of start time. Okay, so this step here might be the most expensive step, but we notice we've got a loop here because now what we're going to do is we're going to go through each class in ascending order of start time now that they're sorted. And starting with no classrooms, we're going to do this step. Now, all I'm trying to do is sort of cash out what we mean here by first compatible classroom. So say we've got our class, CI. Now, if it's compatible with one of the classrooms we have, add C to that classroom. We're done. I haven't really said how to check if it's compatible. I haven't said what order we're going through the D classrooms. That's critical here. There's sort of a hidden loop, maybe. There's a hidden something going on here. How did I go check it with all D classrooms? Okay. Now notice our first time going through, D is 0, so there's no classrooms to check with, so there's no compatible classroom. So otherwise, if there's no compatible classroom, we'll open the next classroom and add it to it. So we really have two possible cases when we're considering a class. Either it fits in one of the classrooms we've already got. Great, we fit it in there. If it doesn't, we'll just open a new classroom and it'll be the first class in the new classroom. Okay, so that's bringing a little bit more detail in because now we can say that this loop, we haven't got a loop here, but it's hidden in this line. There's going to be a couple loops probably. This is some kind of sorting procedure. So when are we going to, or how long is it going to take to do that? Well, it depends on our choice of sorting procedure, but let's assume our n is large enough that we're going to choose an efficient sorting procedure like merge sort, quick sort, heap sort, whichever one's your favorite, and n log n runtime. So that means this effort is going to be n log n time, and then the loop is the rest. Now, it really, well, let's just do a naive assumption here. So I've got C classes. I have to go through my D classrooms to check to see if each one's compatible. I'm going to wave my hands at what it takes to check compatibility for a second, assume it's a constant amount of time. Then at least I've got n, because we have n classes here, n times d, right? N times d, where d is the number of classrooms we use total. Well, in the worst case, we use n classrooms. So this could be n times n squared. So again, let's go back. We know our operation to start out, our sorting operation, n squared if we do it with like a bubble or an insertion, but n log n if we do it, with an asymptotically more efficient algorithm. And this loop here is looking like naively n squared. Okay, now I'm going to leave it at this. Sorting C is going to be n log n. The number of operations carried out by our loop depends on how clever we can be. And so what I just said is naively, we've got sort of an n squared performance here. But let's see if we can be not so naive. Let's see if we can be clever and take this to an n log n. So again, not too much new here, but all it says here is that inside this loop, what we seemingly need to do is for all D rooms, we need to check compatibility. So let's focus in, what does this mean? What do we need to do to check compatibility? And it's actually going to be here, or at least this is one place, where the sorting of our classes is going to become helpful, at least in our analysis. So first of all, let's just say we have a class, CI. And at the moment, we just have one of our previous D rooms, and we're trying to check to see if it fits in that room. Okay. Now on the surface, again, naively to start out, what this means is we need to check to see if any of the classes already in that room overlap with our new class CI. So we could go to each class in that room and check for an overlap. Okay. Now, here's the thing. Here's where we're going to start by bringing in, hey, we know our C is in ascending order. So what that means is all the classes added to this room already, so when we're checking for compatibility, we know all the classes added to this room were added before this class. And since they were added before this class, they must have had an earlier start time. Okay? So all these ones started before us. So what that just means is we need to now just make sure that they all finish before our current class. Okay? And just for the moment, I want to rule out, we don't have to check to see if any of them are compatible. That was already done, right? So all these other classes we know are already compatible. So all we just need to make sure is that all of them finish before we start. That way we know we're compatible. Now also, because we already know they're all compatible, all the rooms in there are already compatible, it's only the latest class that we need to make sure finishes before our class. So what that means is for all of our classrooms, as we're going through this algorithm, we want to keep the classrooms in order of their finish time, but the finish time of the latest class in that room. Okay? Because that latest class in that room is the one we need to check against for compatibility. We don't need to check against the other ones. And then the other important thing we'll notice here is when we add a new class to a room, it will always become the new latest class because we're going in this order. So when we add a new class, it becomes the new representative of that room. So the update is very easy there. Okay. And then the last bit, here's where the cleverness comes in. These two steps here only make sure that comparing compatibility between a class and a room is a constant operation. We only need to compare against one class, the last class. Okay. But how can we get away with not comparing all D classrooms? Well, if we keep the D classrooms in order, and we have to use a clever data structure to do that, a binary search tree, if we keep them in a binary search tree, then we can find a compatible classroom if it exists with log n search instead of n search, or more precisely here, log D searching. If there's D open classrooms right now, log D to search the binary search tree with D classrooms in it. And again, where our upper bound, our worst case d might be n, that would be log n. So again, that's going to allow us in this inner loop, since this is the most important operation here, this last bit is constant time, this most important operation, we can get it down from being order d, in the worst case order n, down to order log d, in the worst case order log n. So we can get the inner loop, now the second loop rather, to be n log n, while our sorting procedure can also be n log n. So the whole algorithm of Alice's algorithm is n log n if we can actually get it to work. Now when I say that, when we can actually get it to work, we sort of jumped the gun here. We said, well, let's look at the efficiency of her algorithm before checking to see if it's even correct. Well, sorry, I shouldn't have done it in that order, but I'm also cheating a little bit. I know that this one's correct, so I guess, spoilers, this is correct. So let's see if we can prove it correct. All right, so I do want to prove this correct. Now, this is sort of an in-depth proof, so I want to go over each of the steps one at a time. Now, for the purposes of studying greedy algorithms, I've built sort of this proof structure that I highlighted in our in the last example in the last video. And in this example, I'm going to use that same structure, but I do want to continue to highlight that if you're out there exploring proofs of correctness on the internet, you're probably going to get a much stripped down version of the proof. Now the reason I haven't stripped it down is I want to leave in these important chunks that maybe you're not as familiar with, and maybe your mathematical skill couldn't fill in the background information on your own without having this sort of extra bits filled in. So I do want to fill this in, keeping in mind though that, you know, as you get more comfortable with this, you might want to strip away some of this machinery as well, and instead focus on really what, you know, some computer scientists might say is sort of the meat of the argument, the real chewy bit, the most important clever piece. And that's what you'll usually see in proof of correctnesses that you might find online, is they'll just pull out that one nugget of cleverness and they'll sort of highlight that, leaving up to you to fill in all the other pieces if you don't trust or believe the nugget. Well, we're going to look at all the pieces because I want us to be comfortable and familiar with how to, say, prove this on our own before we start just jumping to that clever nugget. So let's start out. What is our theorem here? Okay, so we've got Alice's first fit algorithm. Now notice here, I could have said her algorithm in one clause, maybe two clauses, but it's starting to get too long for me to write in the theorem, so instead I'm just going to reference the algorithm by its name. Alice's first fit algorithm assigns classes to the minimum number of classrooms. This bit, the minimum number of classrooms, this is sort of pulled out of the problem statement. Okay, we're basically saying, what does it mean to be correct for our problem, our interval scheduling problem? Well, in this case, it was to assign classes to the minimum number of classrooms. So we pulled that right out of the problem statement, but we left a reference to the algorithm here. Go look up the algorithm on your own while we just looked at it. Okay, let's get started. So remember, we want our proof to be general. So to be general means we have to assume we have a input that is arbitrary, that is not a specific input that we just set. We can't just say, assume they give us classes 1, 2, and 3. Look, we give the right output. No, that only proves that we work on that input only, and we need to prove that we work on any possible input, and so we call that an arbitrary input. So we're going to assume we have an arbitrary input here. Okay, and I just fleshed that out a little bit. We could just say, assume we have an arbitrary input. That's vague. It doesn't tell us what we mean. Well, here I say, well, give me an arbitrary set of classes and classes with their start and finish times. That's what I care about. Okay. Again, getting our proof set up, we need, like a program, to define what we're going to talk about. And usually that means set up with some definitions. So I'm going to start with some definitions. I want to talk about my solution. I want to talk about an optimal solution. I want to compare them. So let's grab some. Now, in our last proof, I use S. I often use S to mean solution for my solution. But I've switched to P here, and the reason I've switched to P here is, at least in my problem statement, I've already used S's, and I don't want to confuse myself or my readers by using the same notation for two different things. So I've just just for careful sake, I've decided I'm going to call it P for partitioning in this case. And the way I've sort of written this, I've written P is equal to, and I've used capital P's in here. Normally, when we have elements of a set, we would usually use lowercase letters. But I've used uppercase here because in a partitioning, the members of a set are sets. And we use capital letters for sets. So to indicate, again, to my reader, so that they know this is a partitioning, well, each one of these things are sets then. P1 up to PD are sets of classes. Or more specifically, we could say each one of these are subsets of C. And because we have said that in this word partitioning, each one of these is a subset, and they have those two extra properties we brought in. They're mutually disjoint, and they are together exhaustive. Okay, so I said this is going to be our solution, so this is the one that's supposed to be returned by our algorithm. So this is going to be some D partitioning. Now at the moment I've chosen D instead of M because it's my goal to argue that D is M, that P is optimal, that it splits it into the minimum number of classrooms. But if I assume that right off the bat, when I'm just setting it up, then I beg the question. I've assumed what I'm trying to prove, and that doesn't get us anywhere. So I'm going to give it a different name here, D, with the goal of proving it's equal to M. So the next set I'm going to be looking at here is an optimal set, which I'm still going to call O, and it is going to be an M partitioning, where I've chosen M is the minimum size. Okay, so this is an optimal M partitioning. All right, so the only difference between these two, well, the only difference I've highlighted right now is how many elements there are. We don't know if they're the same. Also, they might be assigning different classes to classrooms, but we'll get to that in a second. Again, I'm setting up here, getting ready. The first point is for generality, the next two to just give me things to talk about, P and O, with some sub bits, D and M as well, showing up as well here. But now I'm going to just give a sort of signpost to my reader. Whoever's following along with my proof, I'm going to let you know what's going on. Okay, just like up above here when I said proof, that's letting you know I'm starting my proof. Here we go. We're into the proof. But here I'm saying, I'm sort of stopping. This might be a comment if I was writing a program saying, okay, reader, listen up. My goal here is to show that these two sets are the same size, that my algorithm assigns classes using the same number of classrooms as an optimal algorithm does. So I'm trying to show M equals D. If I can do that, because that's the criteria of optimality, the minimum number of classrooms, that would show that P is optimal. So my goal is to show P is optimal. I'm going to do that by showing M is equal to D, but the way I'm going to show M is equal to D is actually showing that P is equal to O. If I can show that these sets are exactly equal, then of course D is equal to M. And if D is equal to M, P is optimal, we're done. So again, this is just a signpost saying, hey, stay tuned, this is what I'm trying to do. And in proofs, it's often a good idea, I think I've mentioned this in an earlier video, is the way that I sort of write my proofs. You start out by telling your reader what you're going to do, and then you do it, and then sometimes you just finish off by saying, hey, I did it. And that's just to remind your reader, hey, I told you I was going to do this, I've done it, so now we're done. And in fact, at the end, the QED, that's usually what QED means. It says I've completed what I said I was going to do. Okay. Well, we've said what we're going to do, let's try and do it then. Okay. So now what we're going to do here is we need to think about some cases. Okay. Actually, to get started up, now remember this is where we bring in our pseudo induction. At least this is what I said in the last video. This is where induction should be coming in, but because I don't want to fill in all the details of everything here, we sort of smuggle it in with a quick step. So I'm going to start out here. I'm going to say let Ci, that looks like a classroom, right? Okay. It's going to be the first class in increasing order of start time. That's the order that we would be, that Alice's algorithm is going to handle the classes. This is common in our proof. We usually want to handle the elements of the input in the same order that our greedy algorithm would do it. That just makes it easy for us to make the argument as we go. So we're going to look at each class in increasing order of start time. And we're going to compare where P and O assign those classrooms. or sorry, assign those classes. Okay. And as long as P and O are assigning CI to the same classroom, we ignore them. We stop only when P and O assign CI to different classrooms. That's where our proof is going. Okay, now remember with me why we're going to be doing this. Assuming they agree up until this point, that's sort of the pseudo-induction. That's our inductive hypothesis saying, okay, let's just say it works up till here. Now we're going to argue that it works at this point as well. And that gets our induction rolling. Okay. Now what this also does is it's saying, hey, if there's no such place where they disagree, then that means P is equal to O and we're done. Remember, that's what we were trying to show. P is equal to O. So there's really two cases here, but one of them is so easy we've ignored it. We've swept it under the rug. Okay? We've said, hey, if P is equal to O, we're done our proof. We're trying to show P is equal to O. If they're already equal, we're done. So we're going to start with an assumption here that they're not equal. So there must be some point where they disagree. Now, when you make an assumption like this, there's going to be usually two possibilities. One, that's a foolish assumption. That's a contradiction. So good, that's what we would want. We don't want them to disagree, right? So hopefully if we arrive at a contradiction down here, great, that means they must have agreed. They must be the same, it must be optimal. Good, okay. So one possibility we could get a contradiction. Now for our proof of correctness here, the other possibility is, oh, it's perfectly fine that they assigned it to a different classroom. Okay, now why is this? Well, maybe there's a tie. Okay, or let me put that in another way of saying that. Maybe there isn't just one unique optimal solution. Maybe there's more than one optimal solution. If there's more than one optimal solution, it could be possible that P is optimal and O is optimal. Therefore, our D equals our M. But the way we assign classes to classroom is different. Okay, and I don't just mean all the classes to classroom 1 are assigned to classroom 2 and vice versa. That kind of similarity we can rule out. Okay, we can line them up in a specific order so that we're not just getting an index is mislabeled. So assuming we're not just mislabeling our indexes, we could still have a tie. So a very simple example of that, imagine we have a class that could fit in 2 rooms. Our last class, it could fit in 2 rooms. It doesn't matter which room we put it in. So we could, maybe P puts it in room 1, O puts it in room 2, and now we have a difference in our assignments, even though we maybe both are optimal solutions. So in that case, we can't arrive at a contradiction. So remember, by making this assumption that they're different, one case might be, oh, that's a contradiction, that would never happen. The other case might be, oh, that could happen. And remember, our strategy when it could happen is, let's do what I call a swap argument, where we say, okay, if there's more than one optimal solution, then I was mistaken. It wasn't O that I meant, it was a different one, O prime. Okay, and O prime does agree with us in our assignment, but still optimal. Okay, so those are our arguments or strategy that we're going to try and approach. But to do that, we usually want to break it into cases, because some of those cases are going to arrive in contradictions, so we'll handle them one way, and then other cases we have to do the swap on. Okay, and then some cases, actually, I think we saw this in our last argument, some cases we have to do the swap on, and that gives us a contradiction. Okay, so there's sort of 3 different techniques here. Well, let's get started. Now, I want to think about what different cases we really have for assigning our classroom CI to classrooms here. Okay, now I kind of went over them while we were fleshing it out here. One of them is that case where there's a tie and it doesn't matter. And it sounds like in the tie and it doesn't matter case, we need to make a swap. Okay. There's one other case too that I think is really important. And that's going to be, what happens if we open up a new classroom, right? So in our loop, remember, we had 2 steps. The second one was, oh, none of our classes were compatible, so we opened a new classroom. The case that I think is really important here is, what if we opened our new classroom but we didn't have to? Okay. The idea here being, our D got 1 bigger, but O somehow managed to fit them all in 1 fewer classrooms. So that's the first case I want to handle. Okay. So in this case, the way I've tried to flesh this out, be as precise about stating it, okay? So I could say P assigns C to a new classroom and O does not. Now, that would be great if we were actually performing the algorithm and we were going through it step by step, but that's not how I've set up my proof here. These are not pausing the algorithm at step I. These are the final outputs of our algorithm. This is what Alice's algorithm created at the end. This is just any old optimal solution that we just picked out of the mathematical method. Okay, we just grabbed it out of the realm of the abstract and said, we know it exists, we'll give it a name. Okay. So we didn't perform algorithms to get this. We're just assuming this was the output of the algorithm. So we can't assume we've stopped. So what that means is CI is in some classroom. And I'm going to assume, just for the general sake, that CI is in a classroom that has earlier classes in it and later classes in it. Or at least potentially it does. Okay. So instead of saying CI got assigned to a new classroom, I'm fleshing that out by saying CI is assigned to a classroom with no earlier classes in it. Meaning, if we had stopped Alice's algorithm when it was performing and got to CI, we would see it would have added it to a new class because it would have added it to an empty class, one that has no earlier classes in it. CI would be the first one we added. Okay. So here I'm saying assume we add it to a new classroom, one that has no earlier classes, but the optimal solution manages to assign it to classrooms with earlier classes. Okay. Now, if you're already saying this hurts my brain, I'm not even sure how this is going to work, it's because we should arrive at a contradiction here. This shouldn't work. If our algorithm is correct, then we're only going to open a new classroom when we need to, right? Which means if we're opening a new classroom and O isn't, then O is doing something wrong. So that's actually how our algorithm, or sorry, our argument is going to work for this algorithm. Okay, so let's see if we can follow it. Okay, so if CI adds this, if we add CI to this new classroom with no earlier classes, then at this point in the algorithm, if we had stopped it, then this is because every other classroom with earlier classes in it has an overlap with CI, because imagine again in the algorithm we would stop at this point and we would compare it to every other classroom that has earlier classes, meaning every other classroom that we've already opened. And the only way we would open a new one following Alice's algorithm is if they were all incompatible. And they would all be incompatible if they overlapped, if they had a class that overlapped with CI. So we know all those classrooms have an overlap with CI. If O adds CI to one of these classrooms, then it must cause an overlap. Well, this is a contradiction, and let's be careful. What is it a contradiction of? Well, we assumed O is optimal. Hidden inside that assumption is that it is valid, but not just hidden, we've got it written right here, that these were non-overlapping sets. So it's impossible for O to add it into this classroom because it would cause an overlap, and we assumed O had non-overlapping sets. So here's that contradiction we got in, basically saying that when we open a new classroom with our algorithm, Alice's algorithm, we have to, because in that step there are so many overlapping classrooms, there are D+1 overlapping classrooms, or sorry, classes, that it is impossible to put those D+1 overlapping classes into D classrooms. So we need that extra classroom. So this is really, so if you actually go out into the internet now and you look up for a proof for this, I guarantee you, you're probably going to get these couple sentences and that's it. Okay, they won't set up the rest of this. They'll jump right to this bit and say, hey, when we open a class, we have to. Okay, and they'll let you fill in all the rest on your own. Okay, so let's go, but let's fill in the rest together. All right, the next bit here is going to be, we could have a couple more cases here, because the way I've set it up here is, the first one is CI is in a new classroom for P, but it's in an old classroom for O. We just said that's impossible. Okay, another possibility would be that O puts it in a new classroom, but P does not. Okay, that one's probably an impossibility too. We could have they both go in new classrooms. Oh, that sounds like that would be a tie. So that wouldn't be a case where they're going into different classrooms. That's a case where they're going in the same classroom. So we've already handled that case. And then the final case is they're both going into old classrooms that had earlier classes in them. Okay, but that one might not be the case that they're going into the same old classroom. They could go into different old classrooms. So I'm actually going to lump the two cases we haven't handled there together into one case. And what that's going to be is, so in this case, it is, case one was we assign our class to a new classroom, one that had no earlier classes, but O assigns it to an old classroom. The case where we assigned it to a new classroom and O assigned it to a new classroom was handled when that's assigning to the same classroom, so we've handled that case. So the other two cases will be when P assigns C not to a new classroom, to an old classroom. But O assigns CI to any classroom, it doesn't matter. So I'm going to ignore where O is assigning it. I'm only going to focus where P is assigning it. So I'm again going to assume P assigns CI to a classroom with earlier classes. That means we find a compatible classroom to put CI in. Okay. Now what we're going to do here is we're going to say, this is where we're going to be doing our surgery argument, our swap argument. And a surgery argument or a swap argument means we're going to grab our optimal solution O and we're going to change it. Okay. Remember, in this case, we're going to assume there's more than one optimal solution and we just accidentally picked the wrong one. So we now want to pick the right one, the one that agrees with us, by changing O, and changing O in a small enough way that after we change it, we can argue it's still optimal. And hidden in there is we still have to argue it's still valid too. Okay, to be optimal means to be valid. So we need to make sure it's still valid and optimal after the change. So here's what the idea is going to be. Let's say we have basically two classrooms that we need to worry about. So in our optimal solution O, we're going to have classroom OI, I'm going to call it, is the classroom that O assigns CI. Okay, so in this optimal solution, there's some classroom where CI gets assigned. I'm going to call that OI. Okay, I'm going to let O sub P, this is still a classroom in O, okay, but it's the classroom in O that P would have assigned CI if we were in P instead. Okay. Now what that means is O sub P has all the same earlier classes as the classroom in P that P assigns CI to. Okay. Now we know it's a different classroom because of this assumption that we've assigned to different rooms. Okay. So we've got OP, the room that we would have assigned CI to, and OI, the classroom that O assigns it to instead. Now remember, in your brain, I want you to think of this as a tie case where we could have assigned it to either room, but we just chose differently. Okay. Now the other thing that's sort of important is we could have assigned CI to either room. We know that because one, O assigns CI to OI, so it must be compatible with OI, and P assigns it to OP, so we know it's at least compatible with the earlier classes in that room. Okay. Now the swap that I'm going to do is not just moving CI from OI to OP. If we do that, we might cause an overlap with classes in OP. Okay. Imagine there were two classes that have the exact same start and finish time. So it didn't matter which two classes we assigned them to. But if we swap one from OI to OP, but not the other one back, we cause an overlap. That makes sense, right? So what I'm going to say here is I'm going to say now take all the classrooms, all the classes that begin no earlier than CI in OI and OP and just swap them. So we're basically going to draw a line in OI and OP right at the starting time of CI. And all the classes that start after that point or at that point, so including CI, we're going to swap from one room to the other. Now why we're swapping all the classrooms is to make sure that there's no overlap created with any of the later classes. All the later classes that we know already don't overlap with each other, so we're going to grab them all as one chunk and swap them into the other one. And then again, in the other classroom, we're going to swap all those classes back out. Now, the critical thing is, because we're using this cutoff point of CI, the starting time of CI, all the classes we swap all start after that point, or exactly at that point. And what we know is all the classes we leave behind must finish before that starting time, because they're compatible with CI. And that's the critical last bit of our argument here. So the first bit, this is the easy bit. Because of this swap, you'll notice we haven't created any new classrooms. We've just swapped classes from one classroom to another and vice versa, meaning we haven't increased the number of classrooms used. So if O was optimal, which it was by assumption, then O prime is optimal as long as we haven't introduced overlaps. If we introduce overlaps, then we've just made something that's not valid, and so it can't be optimal. But if it is valid, that's this last bit here, if O prime, if we can argue it is valid, meaning it has no overlaps, then it must be optimal. So let's see, and I started that argument already, but let's see, can there be any overlaps? Okay, well, because we swapped that whole chunk of classes, there can be no overlaps after CI, we know that part. So could there be overlaps before? Well, as I mentioned, these two classrooms, OI and OP, all of the classes that existed in those classrooms that start before CI, we know are compatible with CI because O adds CI to classroom OI, so we know it's compatible for that reason, but P adds CI to the classroom OP. So we know that CI must be compatible with all those entries in OP as well. So by moving CI and all the later classes into OP, we do not create an overlap because we know all those original classes in OP do not overlap with CI. And then vice versa, all those classes that we took out of OP and moved into OI, those ones all started at the same time as CI or later, so those ones are also compatible with all the original classes in OI. Okay. All right, so I've made the argument, hand wavy. Let's see if we can go through this. I think I've made the same thing. So this is just stating what we need to prove again. I should mention this line here is again sort of a signpost telling us what we want to do now. If O prime is valid, then it's optimal. That's what we want. So let's see if we can argue that it's valid. So how do we know it's valid? Well, it's valid if there's no overlaps. Okay. We could have only introduced overlaps into these two classrooms that we swapped, and all the other classrooms were untouched. So by assumption, they have no overlaps. Okay, let's do this one at a time. OI has no overlaps because all classes added to OI were mutually compatible. So all the new ones we added already had no overlaps between them, and started no earlier than CI. That's how we did the swap. And then all the original classes remaining in OI were again originally mutually compatible by assumption, and finished no later than CI starts. Now here's the part where that extra little bit of argument, how do we know that they finished no later than CI starts? Well, because CI was compatible with room OI, and vice versa, CI was compatible with room OP. Okay, so I've got the OP sort of in brackets here because the exact same argument, exact same wording works for OP as well. Okay. But after the swap, O prime is still optimal by our assumption here, or by our argument rather here. But now it agrees with us on this class. So here we do the swap on purpose because now we can say the only reason that they disagreed was a tie. And effectively our argument says we could settle the tie either way, so let's settle it our way instead, therefore we've got agreement. Okay, now we've really done all the argument, but I want to finish things off by just sort of saying what we did. Case 1 exists or ends in a contradiction, and in case 2 we can modify O so that it now agrees with P. Now imagine there were more places that we disagreed in between P and O. Again, they have to be other ties because this is impossible. If there were other ties, then we say, well, go and make swaps for all those ties as well. So this is saying repeating this argument for every class that disagrees. Well, then eventually we'll get to a point where P is equal to O, and therefore P is optimal. And that's what we're trying to argue here. So the sort of just concluding our proof here is just finishing off saying what we've done here. Okay, and this is again sort of finishing off that induction. Okay, so the proof of correctness argues that Alice's algorithm is correct, so we know it's correct. We've got an n log n runtime for it with our earlier analysis. So let's maybe just finish with just an example on our sample input. So we can imagine the first step is sorting by start time. Now I'm not going to go and move these all around and sort them by start time. We can just see by start time we're basically just going left to right, looking at each class by their start time. So the first one we're going to see here is this class here, and I'm going to assign it to, I'm going to call it classroom red. Okay, next class, this one here, overlaps with classroom red, so we need a new classroom, call it classroom orange. Okay. Again, next one, I'm going to assume it looks like it starts a little earlier than this one. This one overlaps with red and orange, so, and I'm going to call it yellow, so we got classroom yellow. Okay, this one here overlaps with all three, new classroom, classroom green. Next one up here, again, overlaps with all, I'll call it classroom blue. 5 overlaps, call it classroom purple. All 7 overlap. Remember, this is where we drew that line and we said, hey, there was seven classes in this line. There's no way to assign those to anything but 7 classrooms. And indeed, that showed up in our proof of correctness. It was basically saying, hey, look, at this step, when we're opening up this new classroom, we had to open this classroom. And if you tried to add it into any of these classrooms, you caused an overlap. So that was invalid. So again, our proof of correctness, we're right in that step. So gray, going to call this classroom gray. Next starting classroom. Okay, this one here. Now this one is compatible. It overlaps with gray, purple, orange, and red, but it is compatible with green, blue, and yellow. Now, I mentioned in this algorithm it doesn't matter which one we add it to. Okay, but here I'm trying to follow some, so basically it means it doesn't matter what color, yellow, blue, or green, we could color it any color in our example. But I'm trying to think, what would the implementation do? Which one would it pick? Well, it depends a little bit on which implementation. Did we do the naive one, the n squared one, or the clever one, the n log n one? If we did the clever n log n one, it's probably going to do best first fit, meaning it's going to find the one that it fits best in, the one that has the finish time closest to the starting time. And so that's green, so I'm going to call it green. Okay. Next up, I'm going to assume it's this one. It looks like it's a tie, but I'm going to assume it's this one. Again, using that same strategy, I could add it, not green, I overlap with green, gray, and orange and red, but purple, blue, and yellow, but I'm going to assume best first fit, so I'm going to get purple. Next one up, okay, overlaps with green, gray, purple, orange, and red, but not blue or yellow. Closest looks like blue. Okay, this one overlaps with purple, green, and blue here, but not any of the others. So we'll add, closest one looks like orange. Orange, okay. Okay, continuing, looks like this one here overlaps with orange, but compatible with everything else. So it looks like these look like all ties here. I'm gonna pick purple just because it was in the purple line. That really depends now on how your binary search tree splits handles ties. And so I guess I'm assuming maybe linked list. I don't know. Explore it. See what would result in this order. Okay, next up, it looks like this one here overlaps with purple, but all the other ones are fine, but orange looks like the closest, so I'm going to go orange again. Next up, Careful of this one here. Okay, this one again overlaps, looks like orange, yes, purple, green or blue. I'm going to pick green. Again, following that maybe linked list queue kind of ordering here. Next up, this one here overlaps, looks like with orange, overlaps with purple, overlaps with green, doesn't overlap, looks like blue, so I'm going to pick blue on this one. All right, this one overlaps green, blue, orange, but first one doesn't overlap with, that's orange, so it looks like gray. Oops, I missed. Okay, this one overlaps with green, blue, and orange, but not a purple. So looks like we get a purple. All right, next one. Next one here. Looks like overlaps orange, blue, purple, green, but not gray. This is orange. I'm going to say gray wins that one. Okay. Next one. Orange, blue, purple, green, gray. Looks like red. Okay, next one up. Okay, orange, blue, red, gray, purple. I'm not really sure. I'm gonna assume that that's an overlap there, although maybe it's not. So I'm calling that an overlap and going with my yellow here. But if you don't think that's an overlap, go ahead and recolor that one green if you like. In any case, that would probably only cause one swap, because now we would get this one, okay, and this one would, looks like, go gray. It fits well with that one. Okay, all right, but let's just be careful. How many colors did we use? 1, 2, 3, 4, 5, 6, 7. So it looks like our 7 classrooms was indeed the minimum. Now these are different 7 classrooms than we came up with at the beginning. Well, maybe that was a optimal solution that came up with a different algorithm. The algorithm we came up with was fudging it. We just move things around, right? And who knows how optimal algorithms or optimal solutions are created. They might be created in any old way, but we can imagine that other solution as being the solution we were comparing against in our proof of correctness. So at each step when we had a disagreement, we said, look, but I bet you could swap your classrooms for my classrooms. And if you want to understand that proof a little bit better, go through it step by step and see the swaps that would happen. Okay. And in fact, I usually do a simple version of this, so why don't I do a quick little version of this? So my quick little version usually starts with this this little example here. Now, in this example, we have 2 possible solutions, right? We've got this one, or this one. So we could imagine that our solution, maybe the optimal solution was the red one, and our solution is the black one. And if we're going to do some comparisons or swaps now, let's say, starting out here, this is classroom 1, right? So in the first case, when we look at our first element, this first one, they agree. They both assign to classroom 1. Okay. So then we go to our next one, this one here. This one we'll call classroom 2. Okay, and again, classroom 2 for red. We see, yeah, this one agrees. They both assign it to the same one. But when we get to the next one here, this point here, this is our CI now. Here's the line we're drawing on the CI. We're saying, okay, so this is now our OP and our OI. Okay, since we give them to the opposite. This is our CI. Our CI is assigned to classroom 1 in our solution, but it's assigned to classroom 2 in the optimal solution. So now what we're saying is go into this classroom. We're going to take all the classes after it, that's this one here, and all the classes that start after it in the other one, and do a swap. After the swap, we're going to have this CI moving down from, it's currently in classroom 2 into classroom 1, and we're going to have or this other one, we didn't give it a name, all these other ones moving into classroom 2 from classroom 1. That's going to put them where they belong according to our solution. Okay, so after the swap, again, they'll be in the black outlined classrooms instead of the red outlined classrooms, which means now the optimal solution, we should call it O prime now, now agrees with our solution, P we called it. Okay, so again, this is just sort of maybe a visualization of that swap algorithm or argument, and if you wanted, we would have swapped all the other ones that are in there as well. Okay, all the other ones get swapped as well. All right, so that's just intended to be a quick sort of visualization of how the proof actually worked with the swap argument. But that's all I wanted to talk about for Alice's algorithm, and I'm going to leave to the next video Bob's algorithm. So we'll come back and look at Bob's algorithm in the next video. All right, thanks for watching, and we'll see you in the next video.